So my name is Gordon Brown. I'm from CodePlay. I'm going to talk to you today about SYCL and building C++ libraries with SYCL. So first of all, before I start, a small acknowledgement disclaimer. Some of the content in these slides is contributed from other members of CodePlay as well as members of the C++ committee in the Kronos group. So acknowledgements to them. But any mistakes in here, unfortunately, are mine. So CodePlay is a company based in Edinburgh, Scotland. We have approximately 60 engineers. We primarily work in developing heterogeneous solutions for semiconductor companies. We're also very, very heavily involved in standards bodies. So we're involved in the Kronos group, the HSA Foundation, the C++ committee, and also ISO 26262 for safety critical systems. We also have our own product line of implementations of standards like OpenCL, SYCL, and Vulkan that are customized for hardware. So an overview of what I'm going to talk about today. I'm going to start off with an introduction to SYCL, so the motivations behind it, the specification, what the ecosystem looks like. And then I'm going to sort of go into a deep dive into an example of SYCL, how you build it, what the different components are, what it looks like. I'm going to answer some common questions. I'm going to finish up by looking at some C++ libraries that we've been developing and to sort of demonstrate the kind of things that you can do with SYCL. So, first of all, for anyone that's not familiar with OpenCL, OpenCL is a standard from the Kronos group for developing heterogeneous applications. It consists of a host C API and an OpenCL C kernel language for your device code. SYCL is a relatively new standard also from the Kronos group. It's a single source high-level C++ programming model that's built on top of OpenCL, and it's standard C++ 14. So the idea of SYCL is to deliver the performance portability of OpenCL to C++. But let's back up a bit first. So why do we want to do C++? Why create a new programming model? Why base this on top of OpenCL, and why should you be interested? So first of all, why would we choose C++? Well, C++ is rapidly becoming the language of choice for heterogeneous programming. To try and demonstrate that, myself and some colleagues, we put together a list of C++ programming models and languages. And so the criteria for this was any C++ language or model that targeted heterogeneous systems. So it wasn't not just multi-core CPUs, but also heterogeneous devices like GPUs, FPGAs. And also, there had to be a language or a model in themselves. It couldn't just be a wrapper. So we took this list and we mapped it out against the years that they were released in a graph. And this is what we came up with. So this is not a definitive representation, it's simply an approximation based on the list that we came up with. So what this shows is that since around 2003, there's been a steady increase in heterogeneous programming models and languages for heterogeneous systems, particularly in C and C++. Another graph with the same data. This shows that for a long time, C was the dominant language for heterogeneous programming. However, in recent years, C++ has rapidly overtaken that. So you may wonder why there's other programming models out there, things like C++ AMP, CUDA, OpenMP. Why create a new standard? So the reason for that is that there's many other standards. SYCL is the first entirely standard, entirely portable programming model. So the best way to describe that is if you look at an example of CUDA. Here in CUDA we have this global attribute that's used to annotate a function to say this is a device function. And then below that you have this extended syntax with the three ankle braces to say you want to execute this function. And then an example of OpenMP, you have these pre-processed macros preprocess pragmas to say that, to give a hint to the compiler to say you want to parallelize this loop. And then this is an example of C++ AMP. And C++ AMP, you have this restrict keyword that you use to decorate a lambda to say this is a device function. But in SYCL, you don't have any attributes, there's no extended syntax, there's no pragmas, there's no extra keywords. It's just entirely standard C++. So any SYCL application can be compiled with any standard C++ compiler. There's no exceptions. So why did we base it on top of OpenCL? So the reason for that is that OpenCL already has a wide range of support for heterogeneous systems. Not just CPUs and GPUs, but also APUs, accelerators, FPGAs, DSPs, and many more. There's the number of heterogeneous systems that OpenCL supports is growing all the time. And with every new vendor that supports OpenCL, that's another new vendor that can potentially support SYCL. So basing SYCL on top of OpenCL makes it much more future-proof in terms of portability. So finally, why should you be interested? Well, heterogeneous computing is everywhere. It's driving the technology of the future. You see it in self-driving cars, in drones, in speech recognition, animation, games, medical imaging, and telecommunications. It's becoming more and more important. So this is an overview of what the SYCL ecosystem looks like. So generally, you'll have C++ applications. They'll use C++ templates. In these template libraries, you'll have SYCL device functions. These SYCL device functions will execute on OpenCL-enabled accelerators using the OpenCL runtime. But for this talk, we're primarily focused on SYCL and the libraries that are built on top of it. So this is an overview of the SYCL specification roadmap. So everything I talk about today will be based on SYCL 1.2. And you might wonder why it's SYCL 1.2, not SYCL 1.0 for the first version. And that's because the versioning of SYCL follows the OpenCL versions that it supports. So SYCL 1.2 supports OpenCL 1.2. And SYCL 2.2, which is currently in the provisional stage, so there's a provisional draft that you can see on the Kronos website. This is based on OpenCL 2.2, and any future versions of SYCL will support future versions of OpenCL. So some of you might have also heard of the C++ kernel language. And you might wonder sort of why does Kronos have two standards for C++? And are these competing standards? And the answer to that is no, that's actually the opposite. There's two separate standards that have their own use cases, and the Kronos group are actually trying to sort of actively converge them together to have them similar as possible. So what's the difference though? So traditionally, OpenCL was always a C-based kernel language, so all your device code was in C. However, with OpenCL 2.2, you now have a C++ kernel language. But it's still a separate source programming model, so you still have a separate host code and device code, and you still have the same host C API. And it's still very low level. Whereas SYCL is a higher level single source programming model, so all your host and device code is in the same source file, and it provides a much higher level abstraction that removes a lot of the boilerplate code of OpenCL and does a lot of optimizations for you. Yep. So next I'm going to show you an example application of SYCL and how that works and what the different components are. So for this example, I'm going to do a simple vector add. So the first thing you need to do is you need to include the SYCL header file. So the entire SYCL runtime API is included in this single header file. I'm also using importing the namespace just to make the slides easier to follow. So the first thing you need to do in SYCL is you'll want a device to execute work on. So in order to do that, you use what's called a device selector. So a device selector is essentially a function object. So it can be a lambda, it can be a functor. And the function call operator of the function object provides a logic for selecting devices. And it does that by providing a score for each device. So then you pass this device selector to the SYCL runtime. What the SYCL runtime does with it is it will query your system for all the devices you have available, and then it'll feed it through this device selector, and then it'll give each device a score. And then the runtime will pick a device based on the highest score. So this allows you to do things like you can have a device selector that will say, for example, I want a GPU from this vendor that supports double type. Or maybe you say I want to have a device, an FPGA device, or if not, fall back to another device. So it allows you to do very sort of complex logic for choosing devices in a very sort of simple, concise way. So we go back to the example. We create a queue. So in SYCL, the object you need to enqueue any work is a queue. And there's many different ways of configuring a queue. The simplest way is to simply the default construct a queue. And what this does is this uses the default selectors, one of SYCL's built-in selector types. And that will have the runtime choose a device for you. So the next thing to do, you need to enqueue work on this queue. So you do this using command groups. So a command group is essentially a collection of asynchronous operations that are required in order to perform a computation on a device. So it contains three things. There's a device function, a range of execution you want to execute across, and a number of accessors. And accessors define your memory access dependencies. And what these command groups allow you to do is define dependency-based task graphs. And we'll talk about that a little bit more than that in a moment. So back to the example, we create a command group by simply calling submit on the queue. And to the submit function, you pass a function object. And again, it can be a lambda or a functor. And the parameter of this function object is a handler. This handler is a command group handler. This is essentially links the different parts of the command group together. So next, now that you have the command group, you need to get some memory onto the device. And in SYCL, we have a unique way of managing memory in that the storage and access of the memory is separated into this relationship between buffers and accessors. So first, you have a buffer. A buffer manages memory across the host and one or more devices. So a buffer will likely have quite a long lifetime in your application, and it can be used across multiple devices throughout its lifetime. The accessor can be constructed from a buffer, and it's a much more lightweight object, and it essentially describes an instance of access on a particular context. So it describes where and how you want to access the memory that's managed by the buffer. And this accessor is constructed within the command group for a particular device. But you can have multiple accessors from your buffer, so then you can also see you can have another one to access on the GPU, for example. And the buffers and accessors are type safe. So this provides type safety when you're passing data across to the device. So what this relationship between buffers and accessors allows you to do is allows you to create data dependency graphs for your command groups. So an example of that is, say for example, you have 4 buffers and 3 command groups. Command group A reads from buffer A, writes to buffer B. Command group B reads from buffer A and then writes to buffer C. And then command group C reads from buffers B and C and writes to buffer D. Now all we're doing here is just describing the command groups and the memory they want to read and write to. It's just defining the requirements. But from this, the runtime is able to build a dependency task graph from this in order to deduce that command groups A and B can run in parallel because there's no dependencies between them. But command group C has a dependency on A and B completing because command group C is reading from buffers that are being written to by previous command groups. This is just a simple example, but it shows the idea of how these task graphs can be built. So some of the benefits of these task graphs is that it allows, because you define your problems in terms of relationships, it removes the need for explicitly defining copy operations or having complex event systems for handling the relationships between your device functions. It also allows the runtime to be able to do some smart data movement optimizations. For example, it can preemptively move the data to a device if it knows you're going to need it there, or it can avoid copying it back to the host if you're going to need it on the device later on and it's better to leave it there, or it can avoid copying data if you're not going to need it. So back to the example, so see what this looks like. So here we create 3 vectors, standard vectors, 2 inputs and an output, and we initialize it with some data. Then we create 3 buffers, a buffer for each vector, and the buffers have a type and a dimensionality associated with them. So these are one-dimensional float buffers. And we construct it with a pointer and a range. And the pointer and range are the pointer and size of the vector objects. The next thing we do is we wrap a scope around the buffer. And the reason we do this is that in SYCL, buffers synchronize based on RAII. So when a buffer is destroyed, it will block and wait for any command groups that are dependent on it to finish before it returns. So after a buffer is destroyed, you can be guaranteed that the data is synchronized again. And finally, we create the accessors. And the simplest way to do this is to simply call get access on a buffer. And here we use a template parameter to specify whether it's read or write. So for the two input buffers, we get read accessors. And for the output, we get a write accessor. So the last part is that you need to define your actual device function, the work that the computation you're going to do. In SYCL, there are several ways that you can describe parallelism. In the top left corner there, you've got a single task. A single task executes your device function exactly once, and it doesn't take any parameters. In the bottom left, you have parallel for. This executes your device function over a range of work items. And the range is defined here. So, for example, the range is here is a two-dimensional 64 by 64 range. So your device function will be executed 64 by 64 times, and the parameter is an ID. So the ID represents the index into the workspace you're executing across. On the right is another one we have called the hierarchical parallelism. This is a little more complicated, but in order to describe this, it's good to look at the execution model and memory model of OpenCL. So in OpenCL, all hardware is split up into work items and work groups. So work items are essentially threads of execution, and these are grouped together into work groups. And the important thing is that there's memory that is local to work items, and there's memory that's local to work groups. And what this way of representing parallelism allows us to do is, because there's nested parallel fors, the parallel for work group and the parallel for work item, if you have everything that's in the parallel for work group scope is executed once per work group. Everything in the parallel for work item scope is executed once per work item. And then any variables you declare in the parallel for work group scope, they're local to a work group. And any variables you declare in the parallel for work item scope, they're local to a work item. So it allows you to better represent the parallelism of OpenCL. For this example, we're just going to use a parallel for add, which is the most common use case. So here we pass parallel for with the range, and here we're going to do the range the same as we did for the accessor, so one-dimensional range using the size from the vector. And then we have the device function. This device function is very simple. It's just simply reading from A and B, adding them together, and assigning it to C, the output, sorry. In order to index the accessor, you use the subscript operator, and you pass this the ID parameter for the parallel for. One thing you'll notice is that the parallel for has a template parameter there. The reason for this is it'll become clear later on why this is important, but sometimes it's important for the SYCL runtime and the user to be able to identify a device function. Now, if your device function is a functor, then that's simply the name of the functor, but if it's a lambda, you need to provide a name for it, and that's what that's for. So finally, we wrap up our code in a function, a library function, that instead of initializing the vectors, we're simply passing these in as parameters now. And there's an example of calling the function. So you initially construct two input vectors, an output vector, and pass them to the function, and by the time this function returns, your result is stored in the output vector. So now that we have the device function, the next thing we need to do is we need to compile it. So SYCL is a single source programming model. So the best way to describe that is to first look at the C++ compilation model. So you have your C++ source file, you pass it to a CPU compiler, and you get an object. You link that object, and you get an executable, and that's run on the CPU. What happens if you also want to compile code for a GPU as well? There's generally two ways of doing this, and the first is separate source, like OpenCL, and there's single source, that's SYCL. So first, separate source. So the example here we have here is OpenCL. So on the left you have the host code, and on the right there's the device function. So the way single source works is you have a separate device source file alongside your host source, and that's passed into the OpenCL compiler, which is linked with your executable through a shared library. And this generates your device executable that's run on the GPU or any other device. However, the issue with this is that because you compile your device source at runtime, your device source has to be shipped with your executable, which can be a problem for some people. Whereas with single source, as we saw earlier, the device code isn't in a separate source file. It's in the same C++ source file. It's simply the device code is simply the lambda or functor object that makes up your device function and any functions that calls. And the way this works is that the same source file is alongside the host compiler. It's also passed into a SYCL device compiler, and this generates a SPIR. And the SPIR is another standard from OpenSAR from the Kronos group. It's this standard portable intermediate representation. So this allows you to compile to sort of a standard intermediate representation that can then be lowered to a vendor-specific instruction set. Now, SPIR allows SYCL to be very portable because any OpenCL implementation that supports SPIR can support SYCL. However, SYCL doesn't mandate that you have to use SPIR. SYCL can be implemented with any binary format intermediate representation that an OpenCL vendor supports. So, for example, you could have a SYCL compiler that generates PTX and then have the NVIDIA's OpenCL that supports the PTX format in order to run on NVIDIA GPUs. So we link the SPIR object together with the CPU object, and then we have a single executable with the SPIR embedded inside it. And that will run on the CPU and your GPU. Oops, it's gone out of sync. Sorry. Oops. Oh, that's it. Sorry. Okay. So let's go back and
Shift F5.
yeah.
And then you'll be synchronized again.
Nice. Seems to be pointed wrong place.
I think what happens is you move the pointer. Now you're good.
Okay, thank you. Sorry about that. Oops. Try that again. Okay, sorry. So, okay, let's go again. Sorry. Current slide. Okay. So next I'm going to go into some commonly asked questions with SYCL. So the first one is can you template your device functions? And the answer to this is yes. So in SYCL, you can template device functions simply by templating the surrounding context. So in order to template this function, we simply template this parallel add. And now you take a SID vector of type T, and the buffers are constructed with type T as well. The difference here you'll notice is that the parallel for type is also now T. The reason for that is that, like C++, SYCL also follows the one definition rule that you can't have two kernels of the same name because it will cause a conflict. So you have to name your kernels appropriately so they don't conflict with each other. So if we go back to the original example where we called the parallel add function, we can now create our own type, my type, and then you create vectors of this type, and then you call the parallel add, and this will instantiate your device function for that type. And this will generally work for any type with some caveats that the types that you pass to device functions in kernel in SYCL have to be a standard layout. And the reason for that is that because you're compiling the code for a host and a heterogeneous device, and for a different architecture, you need to be able to make guarantees about the layout of the memory. So the next question is, can you debug a SYCL kernel, SYCL device function? So debugging heterogeneous devices is probably a talk in itself. It's a very, very complicated thing, and it's still being figured out. Generally, you'd require a debugger for the particular device. However, in order to make this easier, SYCL provides what's called a host device. So a host device is every SYCL implementation is required to provide a host device that doesn't run through OpenCL. It actually executes in C++, but it follows the same execution model and memory model of OpenCL. So although you can't debug on the device itself, you can debug your application, your device code, with the same guarantees that it will execute the same and return the same result. And the way you do this is you simply construct your queue from a host selector. The host selector is another one of SYCL's built-in selector types. It simply just returns out the host device. So the next question is, can you stream text from the device function to standard out? And SYCL does support the printf from OpenCL, but since it's C++, we also introduced a stream object, which is very similar to the stdo stream. The main difference is that it's a buffered stream object. Because you're copying data back and forward from the device to the host, you need to give it a size. So here we initialize a stream object with a size, and then we pass it into our device function. And you can use the C++ stream operators to stream text to the stream. The one nice thing about this is that in addition to basic types like strings and integers, etc., it also allows you to stream types that are normally quite a bit of a pain to print out, things like vectors and IDs and ranges. It makes things a bit easier. And that's the output we get from that. So another question is, what happens if a SYCL device function fails? For example, if you run out of resources on the device, or you hit an exception or something like that, these things can happen. You want to make sure that your application can still continue executing. So SYCL provides a fallback queue in order to allow this. So the way you do this is you simply construct a second queue, and you pass this queue to your command group. So here we have a default queue that will pick a device, but if this device fails, it'll fall back to the host queue. So the SYCL runtime will attempt to recover and then run the same device function on the host instead. Okay. So finally, I'm going to talk about some of the C++ libraries that we've been working on in order to demonstrate some of the things that you can do with SYCL. So there's four I'm going to talk about. These are all still work in progress. Some are various different stages of development. Some of them are open source projects that anyone can contribute to. The first one is SYCL Parallel STL. Some of you will be familiar with Parallel STL. It's the parallel equivalence of the standard library algorithms. It's developed by the Parallelism TS within the C++ committee, and is recently accepted to C++ 17. And SYCL Parallel STL is simply a Parallel STL implementation based on SYCL. This is a list of the parallel algorithms that Parallel STL provides. It's not all of them, but there's quite a few. Not all algorithms are naturally parallelizable. So as an example, I'm going to show a sort and how you use that with Parallel STL, and then how you use it with SYCL Parallel STL. This is a simple sort, vector of ints, and you sort it by passing the iterators, and then you check if it's sorted. So if you want to do this with Parallel STL, you simply switch to the sort algorithm from the parallel namespace, and you pass stdpar. And stdpar is an execution policy. So there's a few standard execution policies, and there's also vendors provide their own execution policies. The execution policy will tell the algorithm how you'd like it to be parallelized. So if you want to use Parallel STL with SYCL, you simply use the SYCL policy, and that's it. And providing that policy will allow it to run on SYCL. But here you're not able to specify a device, so you can also construct your own SYCL execution policies, where you can provide a queue for that to execute on. And you still pass the SYCL policy to the sort in the same way. It's just now it's running on the device in the queue that you've chosen. There's also the SYCL Parallel STL goes a little bit further, and we also provide what's called the SYCL heterogeneous execution policy. What this does is you provide two queues and a ratio, and this allows you to distribute work across two devices. So you construct this execution policy and you pass it to the algorithm as normal. But now, when this algorithm is run, it'll distribute the work across the two devices that you've given it. So the next library we've been working on is Vision CPP. Vision CPP is a compile time DSL for image and video processing. So one of the things that the SYCL allows you to do, because you can template your device functions, is you can create compile time DSLs, which essentially, the way these work is you construct compound types through instantiating operator overloads. So you construct types that represent expressions. And then these expressions can be evaluated all at once. And this allows you to do things like fuse multiple operations together, allows you to optimize away unnecessary data copies, and allows you to evaluate the resources you require for an entire set of operations at compile time. So as an example of this, so you have an expression C equals A plus B. And this A, B, and C can be any type. They could be vectors, they could be images, or they could be objects representing a video stream. Now, when you evaluate this, you have your A and B, your inputs. And then when you evaluate this, construct this addition type. And it's an addition of A and B. And then you have your C that's been assigned to. And then when you evaluate the assignment, you end up with an assignment of C on the right-hand side, which is an addition of A and B. This is a very simple example, but it shows how you can build up compile time expressions as a type. This is an example of Vision CPP. This is still quite a simple example of Vision CPP, but this demonstrates how that works. And this is a simple example that will convert an RGB image to HSV, perform a desaturation, and then convert it back. And in Vision CPP, we have two different types of nodes. There's the leaf nodes, which are inputs and outputs, and the operation nodes, which are the actual parts of the operations that make up the computation. So in SYCL, the green nodes there are the buffers, and the yellow nodes are operations. These can be fused together into a single command group. This is an example of how you'd construct that. Now, this is because Vision CPP is still early in development. This code looks quite complex because Vision CPP doesn't have the DSL front end yet. So what we saw before with the C equals A plus B doesn't have the operators for that yet, but that's still being developed. But this represents how this expression is built up. So each one of those nodes we saw is one of these node types. And this is constructed into a single expression. And then we execute this using the fuse option on a queue, GPU device queue. And then we display the result. The next library we've been working on is SYCL TensorFlow. Now, for those who are not familiar with TensorFlow, TensorFlow is a C++ library for machine learning. So it allows you to create matrices of linear algebra operations, convolutions, in order to do machine learning. And traditionally, it's been CUDA only. However, we've been working closely with Google recently in order to develop SYCL backend for TensorFlow in order to allow you to run TensorFlow on OpenCL devices. And it's recently the SYCL backend has been merged into the mainstream TensorFlow. And it's still a work in progress, so it's still early days, but there's now partial support for OpenCL and TensorFlow. And what this means is that eventually all of TensorFlow will support OpenCL devices. And also it means custom versions of TensorFlow will also work with SYCL. And finally, because we have the continuous integration, that will ensure that no one breaks the SYCL backend within TensorFlow as well. As a sort of overview of what TensorFlow looks like, you have the TensorFlow tensor kernels, which are the C++ libraries built up of eigentensors, matrix multiplies, and convolutions. And these are executed on NVIDIA GPUs through the CUDA C++ and CUDNN, which is CUDA's neural network interface. And these TensorFlows are constructed using a Python front end. Now for SYCL, the only thing that changes is the backend. Now for SYCL, instead of CUDA, we have SYCL and hard-coded OpenCL kernels, and these execute on OpenCL-enabled accelerators. So this is an example of what TensorFlow with SYCL would look like. The main thing up the top here, you construct a SYCL queue, and then you construct an eigen device from that. That's how we interface with TensorFlow using SYCL. Now, here we're constructing tensors, which tensors essentially represent memory allocations, and then we initialize them with some values. And then the tensor maps essentially allow you to view a certain part of a tensor. In this example, we're viewing the same part of the tensor, but so tensor maps allow you to view the tensor in a different way. So you can switch between row and column major, or you can view a slice of the tensor, that sort of thing. And at the bottom there, you see we use this compile time DSL to do a multiply add, and then the assignment will execute that operation on SYCL. Finally, we have SYCL Blast, and SYCL Blast is still very early days, so there's not much to show yet, but it's something we're working on internally. and it's an implementation of the BLAS linear algebra algorithms based on SYCL. So it's still very early in the stage of development, so there's not much there to show yet. But that's something else we're working on. Yep. In conclusion, CodePlay has an implementation of SYCL called Compute CPP, and we're very pleased to announce we've recently released the Community Edition, which is a free version of Compute CPP that anyone can download and try. And so the Compute CPP Community Edition supports Intel CPU and AMD GPU. And at the moment, we have Ubuntu and CentOS distributions of it. Windows will come later. There's also all of the projects that I've been talking about, plus others. There's also TriCycle, which is an open source implementation of SYCL. And we also have an SDK full of integration tools and samples that you can try, as well as the projects that I've been talking about just now. All of this you can see at SYCL.tech. And finally, there is the second International SYCL Workshop. This was being held in February next year in conjunction with PPOP. And the call for papers closes at the start of December. For more details, you can see the link there. Yeah. In conclusion, SYCL is an open source standard programming model that's based entirely in standard C++14. It lets you target a growing range of heterogeneous devices, and it aims to be a foundation for building C++ template libraries that can execute across these devices. And it's available for free to try today. Thank you. Any questions? Sure.
You said that yeah, I'm sorry. You said that the destructor is blocking on. Wouldn't that be a good way to make some pretty hard to find bugs, especially if you don't have a debugger?
Not particularly. So the question was, if would it be difficult to debug the blocking on the destructor of the buffer? And so it's not the only way that you can synchronize. You can also synchronize explicitly by calling a wait on the queue. So there's other ways to do it too if you're finding it difficult to debug the destructor of the buffer. So yep.
Hi. You say it's based on standard C++. Does that mean that you can also have one compiler for one module and another compiler for the SYCL module?
Yes. So the question is, can you have the device function in a different source file from the original code, or have multiple kernels in different source files?
And mix compilers, if it's a big project where you have some modules and you want potentially to...
Okay. So the question is, could you have...
something that CUDA does not support, basically.
So the question is, can you have multiple SYCL compilers compiling for different architectures, different code for different architectures? You can have that, yes. So the build system of SYCL is very flexible. So you could have multiple SYCL compilers compiling either the same code or separate code for different devices. And then the way that that's linked up is how you design the build system surrounding SYCL. So the standard aims to allow a lot of flexibility in how you build it. So you can also have, so the way I described it there, you had a separate host and device compiler. You can also, if you want, have a single driver, single compiler. This is slightly less flexible, but it may be easier for some people. And then with that, you can have the single device compiler, single compiler doing both. So the specification is very flexible to allow it to be implemented in many ways.
So I have a question about defining your own execution policy, like for the parallel STL algorithms. Is there some way, say, if you are targeting an Intel CPU, can you take things like thread affinity and cache partitioning into account? Is it possible to, for instance, use this in the execution policy in some way?
So the question is, can you take into consideration...
So when you create your own execution policy, can you use features like thread affinity if you would like to partition your data so that particular group of threads operates on a given data, and partition the cache perhaps using something like cache allocation technology on Intel? Is that the way to sneak it in if you would like to make use of that.
What you can do in parallel STL will depend on the execution policy used. So the standard execution policies for C++ would allow you to do these things. However, the SYCL execution policy, because it executes on OpenCL, it will be restricted in terms of the features that OpenCL supports. So you can use OpenCL built-ins and SYCL functions, but you wouldn't be able to use CPU intrinsics or anything like that, or in a SYCL kernel. SYCL
Thank
device
you.
function. Cool. No? Any others? No? Okay. All right, thank you.